Good morning, everybody. I will get to the point. For today's class, I'm going to derive a couple of formulas. And then you will use those formulas to solve problems. So we are talking about how to find the arc length using integration. Let's say these derivations are in your textbook, but it is important that you know how to derive them, because in the exam you will not have them in the formula sheets. Okay, the formulas that we will derive will not be in your formula sheet in the exam. So it is important that you understand how to get them. Okay, so we are trying to find, let's say you have a function f of x, y equal f of x, for instance, this function, and we need to find the length of the arc from a point, say here, to a point here. We need to find this length. So this is the function y equal f of x, for example. We need to find that length from a point P to a point here. I don't want to call this Q because I need to call another point. Oh, just call it Q anyway. So we need to find a formula that we can use to find this length here. The point P has coordinate x1, y1. And this one has coordinate x2, y2, for example. So here is x1. Here will be x2. A way of finding this, I need someone to suggest how we can do it. A possible method to find this length from here to there. What can we possibly do? A suggestion, maybe. Sort. What do you think we can do in this case? Sort.
No idea.
No idea? Anna Jung?
No idea.
Dear, what do you think?
Integral root 1 plus dy dx square.
No, I'm trying to ask you maybe an explanation, some technique we can use, not a formula we can use, okay? I'm trying to ask,
no idea.
like, from your knowledge of mathematics, what technique can we use? You have studied, for example, you have studied the parallelogram, the trapezium rule. We have studied summation. So what I'm trying to say is, for example, we can approximate this length into small pieces. We can start here and maybe take a point nearby. We can take a nearby point and we find the length of this. We take another nearby point, we find the length of that. We take another nearby point, we find the length, and then we sum up all the lengths that we have found. All right? If there is a way to find those lengths, you will see that if you take a point very close to P, for example, take a point here, say T here. If you zoom in on that point, it will be a straight line. The curve will be a straight line. If you take any curve, you take a point here, you take another point near here, and you zoom in on that point. If this point is very close to this one, then this length here will be a straight line. Okay? It will be a straight line. And this straight line, we can call this a small change in S, delta S. So this is your point P. Excuse me, this is your point P. So you take a point here by P. And then the length of the arc will be delta S, and it is a straight line. And actually, X will change by some amount, delta X, and Y will also change by some amount, delta Y. Delta S is a small change in S. The arc length will be called S. This whole length is S. So what we are saying is that from this rectangle, triangle you have here, we can see that delta S squared is delta X squared plus delta Y squared. Just Pythagoras' theorem. This is a triangle, so we can have that relationship. We can now divide by delta X. So we are going to have delta S over delta X squared. We divide by delta X squared. This will be the same as 1 plus delta Y over delta X squared. And now, the idea is that we need to take the point T very, very close to P. If it is very close to P, almost like it is the point P, then delta X will be going very close to 0. The small change in X will be very close to 0. And from your knowledge of differentiation from first principle, if delta X gets very close to 0, then delta S over delta X becomes ds over dx. also delta y over delta x becomes, I shouldn't use that, 2 arrows, becomes dy over dx, dy on dx. This is how we, I don't know, you studied P1, this is how you got to the idea of differentiation. The idea that a small change in x becomes close to 0. This means you take, that's why I was asking you guys some ideas on how to solve this, because I know you studied, when you studied differentiation from the beginning, you had to use the idea of taking small changes and adding them up. So this equation here then becomes ds over dx squared equal 1 plus dy over dx squared, giving us ds over dx should be square root of 1 plus dy over dx squared. So the derivative of the arc length is square root of 1 plus the derivative of the function squared. But that's not what we are looking for. We want to look for the whole arc length. That gives us ds equals square root of 1 plus dy over dx squared dx, right? I think you guys should know where we are heading to now. Now, we can add up all of the small changes, add them up, very small changes, we add them up. As we are adding them up, we'll be getting the total length S. And integration is just a summation of small changes. Or in other words, you come here, if you take integral of ds, that will give you integral of square root of 1 plus dy over dx squared dx. And when you integrate ds, you will just have s. S is integral from x1 to x2 of square root of 1 plus dy over dx squared. So all we need to do is first differentiate the function and then square the derivative, and then use this formula to find the arc length from one point to another point. All right? This is the Cartesian form. If your function is given as y equal f of x. Now, I said that in your exam, you will not have this formula in your exam, in your formula sheets. And you may not have so much practice on it so that you will be able to remember it very easily. So how can you easily get it? What you should remember before your exam is this. You don't need, when you go through the derivation, you don't need to go through all this process. all you can remember is that ds, remember this, ds squared is equal to dx squared plus dy squared. ds squared is equal to dx squared plus dy squared. That is the same, is the equivalent of this, but when x becomes very small. So you should remember this, and then just tell yourself when you divide by dx squared, you have ds over dx squared equal 1 plus dy over dx squared, leading to this formula, leading to s equal integral of square root of 1 plus dy over dx squared dx. It may also be stated in this form. You can also write this formula in this form. S equal integral from x1 to x2 of square root of 1 plus f prime of x squared dx. F prime of x squared dx. Okay, that is it. As we move on, I think you guys should do some quick practice using that formula, very quick. There's not going to be enough practice on it. This is exercise 22C in your book. Find the length of this curve y equal 4 x raised to the power 3 over 2 from x equal 1 to x equal 2. And give your answer to 3 decimal places. So S is integral from 1 to 2 of square root of 1 plus dy over dx squared dx. Y is 4x raised to the power 3 over 2. dy on dx is what? 2x raised to the power 1/2. Correct? Yeah. dy on dx squared will be 4x. Correct? So your s will be integral from 1 to 2 of square root of 1 plus 4x dx. How should we solve this? How to find this integral? Ruby? Ruby, what method should we use to find the integral? Ryan?
Yes.
What? You should use substitution. That is where
dy dx goes wrong.
let u be 1 plus 4x. Du will be equal to 4 dx. In other words, dx is du over 4. So your integral s becomes, I will change the limit. When x is 1, u is 5. When x is 2, u is 9. So your integral becomes integral from 5 to 9 of square root of u times du over 4, which is 1 over 4 integral of u raised to the power 1/2 from 5 to 9 du, which is what is that? It should be u raised to the power 3 over 2, right? Times 2 over 3 divided by 4, right? So that gives you 1 over 6 u raised to the power 3 over 2. And then you put your limit from 5 to 9. Okay, you guys, you can simplify that. There is, if your equation is given in parametric form, I would just go ahead and derive this because also you may need this formula in your exam. If your equation y is not equal to f of x, if y is equal to a function of x, you can use the first formula. But if you are given your curve in the form, let's say y equal f of t in parametric form and the x equal g's of t. G's of t. It would be good for you to, you will be asked to find the arc length from t equals something t1 to, from say t, you'll be asked to find s from say t equal t1 to t2. I know some of you may say it will be, you can change it, you can change this curve to the form y equal f of x. However, changing it may result to a more complicated problem to solve. It would be good that you integrate directly from using t. So, what formula should you use here? Let's go back. Remember that ds squared is equal to dx squared plus dy squared. Know that from here, you'll be able to calculate dy over dt, dx over dt. So we will come here and divide all through by dt squared. So ds over dt squared should be dx on dt squared plus dy on dt squared. That gives us ds is equal to square root of dx on dt squared plus dy on dt squared dt. So your s here will be integral of from t1 to t2 of square root of dx on dt squared plus dy on dt squared dt. So this will be the formula you should use if your curve is given in parametric form. Again, I told you guys, you will not be given this formula anywhere, but if you are asked a question about this, you should try to derive it very quickly, starting from here. All the formulas we are going to derive today, or we have derived today, you can start from here and then derive them. So this is the essential to me. You may also see this one written somewhere. It will be written as s equal integral from t1 to t2 of the square root of f prime of t squared plus g prime of t squared dt. And you have to define that f prime of t is dy over dt, and g prime of t is dx on dt. Okay? Sometimes your curve may also be given to you in a polar form. So instead of y equal f of x, and or instead of x equal g of t and y equal f of t, you have your curve in the form r equal f of theta. R equal f of theta. This is the little complicated one. There are two ways to derive the equation for parametric form. You can read about one of the ways in your book. I will show another method, a different method from the one that is in the book, but we lead to the same result. Because I like consistency, so I want to use this method. You also need to start with gs squared equal dx squared plus dy squared. Now, remember that for a curve in parametric form, x is always equal to r cos theta, and y is r sine theta. Now, we will find dx d theta. Dx, 10 minutes left. Dx on d theta will be you leave r, you differentiate cos, you need negative sine theta times r, plus you leave cos theta, you differentiate r, you get dr over d theta. So dx over d theta squared, let's square this. You will square this, you will get sine squared theta times r squared minus 2 sine theta cos theta dr over d theta plus cos squared theta dr over d theta squared. Similarly, you can find dy over d theta. Dy over d theta, you leave r, you differentiate sine, you get cos theta times r, plus you leave sine theta, you differentiate r. So you get sine theta dr over d theta. So dy over d theta squared will be cos squared theta r squared plus 2 sine theta cos theta dr over d theta plus sine squared theta dr over d theta squared. Why am I calculating dx on d theta squared and dr on dy on d theta squared? From here, we will have ds over d theta squared will be dx over d theta squared plus dy over d theta squared. And you can see that your s will be integral from theta 1 to theta 2 of the square root of dx on d theta squared plus dy on d theta squared d theta. Okay, so now we need to add these two, dx on d theta squared added to dy on d theta squared. If you add this will be r squared cos squared theta plus r squared sine squared theta. That will be r squared into cos squared theta plus sine squared theta, which is 1. The second one, 2 sine theta cos theta dr on d theta, and 2 sine theta dr on d theta. This is minus, so this will cancel out. And the third one will be cos squared theta dr on d theta squared and the sine squared theta dr on d theta squared. That will give you dr on d theta all squared. Okay? So it means that the formula for your s will just be integral from theta 1 to theta 2 of square root of r squared plus dr on d theta all squared d theta. Okay, There is no alternative form to this. You have to use it as this. Okay. If you have good memories, you can keep that in your memories. But for me, I like to always find a formula to use if I need it. S is equal to integral from theta 1 to theta 2 of square root of r squared plus r prime of theta all squared d theta. Okay, that is it. We have 3 minutes left. If you will look at the videos, from this class, these 2 videos from this guy, he explains exactly the same thing I'm talking about here in exactly the same way. And this is your work for today. You solve question 2, 5, and question 7, exercise 22C. Because I have already solved question 1. Okay? So we are not going to have a math class today. Those who do mechanics, you will study, you will do the end of chapter exercises, question 1 to 10. Okay? Okay. See you guys tomorrow. Bye-bye.
Bye bye.